Physicists built the most powerful machine in human history to test their best theory of reality. The machine worked. The theory passed every test. And the theory is still wrong. The Standard Model describes 17 particles that build everything you can touch. It predicted the Higgs boson decades before anyone found it. And it cannot explain why the universe exists. We are going to visit a particle that was impossible to observe. A decay so rare it happens once in 10 billion tries. And a crack in physics that 1 in 16,000 odds says is real. If you enjoy the journey, like and subscribe. New chapters every week. Strap in. There is a tunnel buried 300 feet beneath the farms and villages on the border of France and Switzerland. It forms a perfect circle. It stretches 16 miles around, and inside it, right now, particles are moving at 99.9% the speed of light. This is the Large Hadron Collider, and it is the most complex machine human beings have ever built. To understand why it exists, you need to picture what physicists were trying to do. They wanted to smash matter together so hard that it breaks into its smallest possible pieces, the way you might smash two cars into each other at full speed just to see what falls off. Except the cars are invisible. And the crash happens billions of times per second, and the pieces that fly out live for less than a trillionth of a second before vanishing. The tunnel itself took 10 years to build. Thousands of engineers from over 100 countries worked on it. The magnets inside are cooled to -456 degrees Fahrenheit, colder than deep space, because that is the only way to keep the particle beams curving in a circle instead of shooting straight through the wall. When two beams collide inside one of the 4 giant detectors, the energy of that crash converts directly into mass. New particles appear from pure energy, particles that have not existed freely since the first second after the Big Bang. That is what the Large Hadron Collider is doing every single day, recreating the conditions of the early universe in a tunnel under a Swiss meadow. And here is where it gets strange. The machine has been running since 2008. It has collected more collision data than any experiment in history. And the more data it collects, the more it finds things that should not be there. The physicists running it are not looking for proof that their theory works. They already know it works. What they are hunting for is the places where it breaks, because every break is a door. Every crack in the data is a clue pointing towards something the theory cannot see. The detector that confirmed the Higgs boson in 2012 sits inside a chamber the size of a 6-story building. It weighs 14,000 tons. Every second it runs, it produces data faster than all the internet traffic in the world. Filters throw away 99% of it automatically. The remaining 1% still fills millions of hard drives every year. Inside all that data, something unexpected has been building, a signal that physicists spent years trying to explain away, a pattern that kept getting stronger the more they looked. To understand what that signal means, you first need to understand the theory it is breaking. The Standard Model of particle physics is not just a list of particles, it is a complete mathematical description of how matter works at the smallest scale. It tells you what particles exist, how they interact, and what forces hold everything together, and it has been tested more carefully than any other scientific idea in history. But there are things it simply cannot tell you, things that have been missing from the picture for decades. And those missing pieces are exactly what the Large Hadron Collider was built to find. What the team found when they looked deeper changes everything you think you know about the building blocks of reality. Imagine you had a rulebook that correctly predicted the outcome of every experiment scientists ran for 50 years straight, every single one, down to the last decimal place. That rulebook exists. Physicists call it the Standard Model. It was built piece by piece across the second half of the 20th century. Dozens of teams, dozens of countries, experiments running in parallel across Europe, the United States and Japan, each one finding a new particle the theory said should be there. each one confirming that the math was right. The Standard Model organizes all known matter into 17 fundamental particles. Quarks are the building blocks of protons and neutrons. There are 6 types of quarks, and they come in pairs. Leptons are a separate family. They include electrons, the particles that power every circuit and chemical bond in your body, and also neutrinos, nearly invisible particles that pass through solid matter as if it is not there. On top of those, there are force-carrying particles. The photon carries light and electromagnetism. The gluon carries the strong nuclear force that holds the nucleus of every atom together. The W and Z bosons carry the weak nuclear force responsible for radioactive decay, and the Higgs boson gives mass to the other particles. 17 particles, 4 forces, one mathematical framework that ties them all together. The precision of this theory is almost impossible to wrap your head around. One prediction it makes involves the magnetic behavior of the electron. The Standard Model calculated that number to 10 decimal places. Experimenters measured it independently. The theory and the experiment agreed to 10 decimal places. If you measured the distance from New York to Los Angeles and your answer was accurate to within the width of a single human hair, that is roughly the level of agreement we are talking about. The last missing piece was the Higgs boson, the particle that gives all the others mass. Physicists predicted it in 1964. 48 years later, the Large Hadron Collider found it exactly where the theory said it would be. It was one of the greatest confirmations of a scientific prediction in history. So the theory works, and yet, there are things the Standard Model does not even try to explain. Questions it was never designed to answer. Problems that have sat at the edge of physics for decades, waiting for someone to find the door. The Higgs discovery felt like a finish line, the last piece of a puzzle snapping into place. For a brief moment, physicists celebrated. The rulebook was complete, but then the data kept coming in, and something underneath all those confirmed predictions started to show through. A pattern, a discrepancy, a number that kept coming out wrong no matter how carefully the teams ran the experiment. The rulebook may be the most successful scientific document ever written, and it leaves out some of the biggest facts about the universe. What it leaves out is not a footnote. It is the majority of everything that exists. Here is something the Standard Model cannot tell you. What 80% of the universe is made of. That is not an exaggeration. All the atoms, all the stars, all the planets, all the gas clouds, all the galaxies ever observed by any telescope in history add up to roughly 20% of the total mass and energy in the universe. The other 80% is something else entirely. Physicists call the mass portion dark matter, and the energy portion dark energy. The Standard Model has no particle for dark matter, no equation for dark energy. They simply do not appear anywhere in the theory. You can see the effect of dark matter in every galaxy. Galaxies spin, and the outer edges of galaxies spin faster than they should if the only gravity pulling on them came from the visible stars. Something invisible is out there, adding mass, bending gravity. Every large galaxy we have ever mapped shows the same pattern. But the Standard Model cannot tell you what that something is. That is one hole. The second is neutrinos. The Standard Model predicted neutrinos should have zero mass. Then experiments in the 1990s discovered they do have mass, because they change from one type to another as they travel, a behavior that is only possible if they weigh something. This was confirmed. It won the Nobel Prize, and it directly contradicted the Standard Model's own prediction. The theory has never been fully repaired to account for it. Why does neutrino mass matter? Because the mechanism that gives them mass might be the same mechanism that explains why the universe is made of matter instead of antimatter. These two problems may be connected at a level the Standard Model cannot reach. That is the third hole, and it is the biggest one. When the Big Bang happened, it should have produced matter and antimatter in exactly equal amounts, equal and opposite. They should have collided, annihilated each other completely, and left the universe as pure radiation with no particles at all. No stars, no planets, no anything. You exist, which means something went wrong with that perfect balance. Somewhere in the first moments of the universe, matter got a tiny edge over antimatter. Physicists call this asymmetry, and they have a technical term for the property that creates it: CP violation. The standard model does allow for some CP violation. Experiments have measured it, and the amount found is many orders of magnitude too small to explain why matter won. Something else created that asymmetry, something outside the rulebook. 3 failures: dark matter with no candidate particle, neutrino mass with no working mechanism, and a matter-antimatter imbalance so large the entire known theory falls short by a massive margin. The standard model describes 17 particles so well it predicts their behavior to 10 decimal places, and it cannot explain why anything in the universe exists. Something is missing. Physicists have known this for decades. The Large Hadron Collider was built specifically to find it. What they found first was something they had assumed for 30 years was simply impossible to see. Quarks are social particles. They almost never exist alone. They pair up or group together into composite particles, and those composites are what we usually interact with. Protons and neutrons are made of 3 quarks each, but quarks also pair with their own antimatter twins to form 2-particle composites called quarkonia. There is a quarkonium for almost every quark. The charm quark pairs with its antiquark to make charmonium. The bottom quark pairs with its antiquark to make bottomonium. These particles have been studied in detail. They taught physicists a great deal about how the strong nuclear force binds quarks together. They are well understood. For 30 years, one quarkonium was missing from the family, the top quarks version. The top quark was discovered at an accelerator near Chicago in 1995. It immediately stood out. It is the heaviest fundamental particle ever found, weighing about 184 times more than a proton. In the particle world, that is extraordinary. Most quarks weigh a fraction of a proton's mass. The top quark is so heavy it is closer in mass to an entire atom of gold than to its quark cousins. Physicists knew from the day of its discovery that the top quark should, in theory, have a partner. A top antiquark exists. The two should attract each other through the strong nuclear force. They should be able to form a bound state, a composite particle. Theorists calculated what that particle would look like. They gave it a name, toponium, and then they concluded it could never be seen. The reasoning was straightforward. To form a proper bound state, 2 quarks need a tiny amount of time to feel each other's attraction and pull together. Not much time, but some, and the top quark was simply too impatient. Every other quark holds together long enough for the strong force to work on it. The top quark does not. It decays before that can happen. Physicists calculated that the strong force needed roughly a certain window to bind 2 particles together. The top quark's window was 20 times too short. The textbook conclusion was firm. Toponium is predicted by physics, and physics also prevents it from being detected. That conclusion stood for 3 decades. Papers were written around it. Students were taught it. It became one of those accepted limits that nobody seriously challenged because the maths seemed clear. Then a team started looking more carefully at something strange in the collision data. Something that had been sitting there for years, hiding just below the level where anyone had thought to look. The data did not match the prediction, and the gap between them was pointing at something that was supposed to be impossible. To understand why physicists assumed toponium could never be seen, you need to feel just how fast the top quark dies. 1 second is 1,000 milliseconds. 1 millisecond is 1,000 microseconds. 1 microsecond is 1,000 nanoseconds. Keep going down. A nanosecond is 1,000 picoseconds. A picosecond is 1,000 femtoseconds. A femtosecond is 1,000 attoseconds. The top quark lives for roughly 500 zeposeconds, That is 1 level below attoseconds. A number so small there is no everyday comparison that does it justice. The fastest human-made laser pulses ever recorded last about 1 attosecond. The top quark lives 500 times shorter than that. In that time, light travels less than the diameter of a single proton. Every other quark in the Standard Model lives long enough for the strong nuclear force to grab it and pull it into a composite particle. The process of a quark being captured and bundled into something stable is called hadronization. It takes a tiny but specific amount of time, and the top quark decays roughly 20 times faster than hadronization can happen. Think of it like this. Imagine you throw a ball toward a glove. The glove needs half a second to close around it. Your throw reaches the glove in a fraction of that time. The ball passes straight through before the glove can react. That is the top quark. It moves through the window for capture and is already gone before the strong force can lock it in. This is why physicists were so certain. The math was clean. The top quark decays through the weak nuclear force on a timescale that physically prevents the strong nuclear force from completing its work. Hadronization requires more time than the top quark allows. Therefore, no bound state. Therefore, no toponium detectable in any experiment. That assumption held from 1995 to the mid-2010s. Then something happened that shook it. A pair of researchers at a German physics lab were going through CMS data from 2016. They were not looking for toponium. They were studying how often top quark and antiquark pairs were produced at very low relative speed, right at the minimum energy needed to create both of them. At that very low speed, something was wrong. There were more pairs than the theory predicted. A small but consistent excess. The kind of excess that usually means either a statistical glitch or something real hiding in the numbers. They ran the analysis again. The excess stayed. They checked for errors in the detector modeling. Still there. They went back to older data from 2012. The excess was there too. The top quark was not forming a proper bound state, but it was doing something just close enough to leave a fingerprint. And that fingerprint was about to become one of the most surprising discoveries in decades. Science rarely announces itself with a single dramatic moment. Most discoveries start as an itch, a number that is slightly off, a curve in a graph that bends the wrong way, something small enough to ignore, but persistent enough that you cannot quite let it go. The signal that eventually became the toponium discovery started exactly that way. The physicists who first noticed it were not chasing a Nobel Prize. They were doing routine work, checking that the Standard Model's predictions matched what the Large Hadron Collider's CMS detector was actually seeing. Most of the time they matched perfectly. Thousands of checks, thousands of confirmations. Then came the top quark threshold. When the collider produces a top quark and a top antiquark at the same time, the two particles are created with some amount of kinetic energy. Usually they fly apart immediately, but occasionally they are produced with almost no relative speed. They are almost at rest relative to each other, just barely created, almost touching with almost nothing pushing them apart. At that exact threshold, the excess appeared, more pairs than expected, a statistical bump right at the minimum energy needed to produce the pair. In isolation, that bump was interesting, but explainable. Statistical noise exists in all large datasets. Any single anomaly gets a skeptical reception in particle physics. And rightly so. The field has a long history of bumps that disappeared when more data came in. But this one did not disappear. It stayed. It showed up in data from 2012. It showed up again in data from 2016. It showed up in 2017 and to 2018. Every time the team looked, the same excess sat in the same place. By 2024, the CMS collaboration had collected enough data to publish. The excess reached a level called 4.8 sigma. In particle physics, 5 sigma is the gold standard for a confirmed discovery. 4.8 is a hair below that, close enough to publish as strong evidence. strong enough to take seriously. The physicists named the signal toponium, a quasi-bound state of a top quark and its antiquark, two particles that technically should not have enough time to form a pair, but apparently exchange enough force in that brief moment to leave a detectable imprint on the collision data. The skeptics were still skeptical. 4.8 sigma is impressive. It is also 2012 all over again, when a photon excess at similar significance triggered hundreds of papers before it vanished entirely. The question was whether another detector, running independently, looking at different data, would see the same thing. That answer was coming, and the team running the rival detector had no idea what they were about to confirm. Particle physics uses a lot of language that sounds precise, but means almost nothing until you picture it. Quasi-bound state is one of those phrases. It sounds technical. It sounds like something only a specialist could understand. Here is what it actually means. Two particles that attract each other need time to lock into a stable orbit. If you give them enough time, they form a proper bound state. A stable composite particle. Think of the Earth and the Moon. The Moon orbits the Earth because gravity had billions of years to establish that relationship. The system is locked in. Now imagine two objects flying toward each other, attracted by gravity, but they are moving so fast that they whip around each other and fly off before any stable orbit can form. They felt each other's gravity. They pulled toward each other. Their paths bent, but they never stayed together long enough to be called a bound system. A quasi-bound state is something between those two cases. The two particles feel the force pulling them together. They begin to respond to it. In quantum mechanical terms, they exchange a handful of the particles that carry the strong nuclear force, called gluons. The attraction is real, but the system falls apart before it fully locks in. What makes this detectable is a property of quantum mechanics. When two particles almost form a bound state, the energy distribution of their decay products shifts. The curve that describes their combined mass changes shape. A small peak appears right at the threshold energy. That peak is the fingerprint of the quasi-bound state. Think of it like striking a bell that cracks before it can ring fully. The crack still produces a sound, a shorter, messier sound than a full ring, but a sound with a specific frequency that tells you something about the bell. The peak in the CMS data was that sound. The top quark and antiquark did not form a stable particle. They coupled just long enough, exchanged just enough gluons to leave a signature that stands above the background noise of the collision data. What makes this discovery scientifically significant is what it teaches. Quarkonia are among the cleanest systems for studying the strong nuclear force. The force that holds atomic nuclei together is one of the least understood of the four fundamental forces. It behaves in ways that are extremely difficult to calculate. Studying new quarkonia gives physicists precise measurements to test those calculations against. Toponium sits in a mass range that no previous quarkonium reaches. And because the top quark interacts with the Higgs boson at almost maximum possible strength, the quasi-bound state may carry information about that interaction too. Two particles, almost bonded, already decayed, but leaving behind exactly enough to rewrite what physicists thought was impossible. And the rival detector was about to find the same fingerprint in completely separate data. July 2025, the ATLAS collaboration, the second major detector at the Large Hadron Collider, publishes its own analysis of top quark pair production near the threshold. ATLAS and CMS are competitors. They share the same tunnel. They share the same particle beams, but they use completely different detector technologies, different analysis software, and different teams of physicists. Any result confirmed by both is extremely unlikely to be a statistical accident. ATLAS found the same excess, same location, same shape, independent confirmation. That alone would have been enough to make the physics community sit up. But the story did not stop there. By March of 2026, the CMS team had a new analysis ready. They had been studying a different decay channel, a configuration called the lepton plus jet's final state, where the top quark pair decays into one lepton and several jets of particles. This is a different mathematical signature than the previous analysis, a different way of looking at the same phenomenon, a different set of cuts through the data. The excess appeared again. The significance this time crossed 5 sigma. That is the threshold in particle physics that separates evidence from discovery. A 5 sigma result means the probability of the signal being a random fluke is roughly 1 in 1.7 million. At that level, physicists stop calling it a hint. They call it a confirmed observation. Toponium is real, a quasi-bound state of the heaviest quark ever found, a system physicists assumed for 30 years was physically impossible to detect, confirmed by 2 independent machines in 2 independent analyses. The spokesperson for the CMS experiment said it plainly when the October 2025 measurement was announced. Many physicists long believed this was impossible. That is why the result is significant. It challenges assumptions that have been around for decades. There is a list of composite particles called quarkonia, one for each quark flavor that compare with its antimatter partner. Charmonium for the charm quark, bottomonium for the bottom quark. Now, for the first time, the top quark has its own entry. The family is complete. And what the data revealed about this particle's physical properties made even the researchers who had been working on it for years pause. Toponium lives for roughly 230 yoctoseconds. It has an estimated size of about 60 times smaller than a proton. It is the most massive composite particle ever observed, heavier than the heaviest atomic nucleus on the periodic table, and it holds that record while being almost incomprehensibly small. The heaviest, the smallest, and until recently the one everyone agreed could never be seen. What this discovery unlocks about the strongest force in nature is only beginning to come into focus, and the implications reach much further than one new particle on a list. Every generation of physicists inherits a set of things that are simply known to be true. Established results, settled science, the kind of facts that appear in the first chapter of a textbook, without any caveat or asterisk. One of those facts, for 30 years, was that the top quark cannot form a bound state with its anti-quark. The math said so. The timescales said so. Nobody seriously argued otherwise. That fact is now wrong. The conformation of toponium does not change the underlying equations of the Standard Model. The math that describes the top quark's decay time is still correct. The timescales are still correct. What changed is the understanding of what can happen in the tiny window before the decay completes. Physicists now know that the strong nuclear force can leave a measurable imprint even when it does not have time to lock 2 quarks into a proper orbit. That imprint is detectable if you know what to look for and you have enough collision data to find it. The assumption that the imprint would be too faint to see turned out to be wrong. This matters beyond just adding one particle to a list. Quarkonia are the primary laboratory for studying the strong nuclear force. The strong force is mathematically brutal. It grows stronger as the quarks you are trying to separate get farther apart, which means you cannot isolate quarks and study them directly. You study the force through the composite systems it creates. Charmonium and bottomonium have been used for decades to pin down the properties of the strong force. Each type of quarkonium probes the force at a different energy scale, the way you might test a rubber band by stretching it to different lengths. Charmonium and bottomonium probe the lower energy ranges. Toponium probes a range that has never been accessible before, a regime where the strong force coupling constant behaves in ways that are much simpler to calculate. That means cleaner measurements, more precise numbers, better tests. There is also a connection to the Higgs boson. The top quark has a property called a Yukawa coupling, which describes how strongly it interacts with the Higgs field. That coupling is nearly 1, the maximum possible strength. No other fundamental particle is as tightly linked to the Higgs as the top quark. Studying the quasi-bound state of the top quark and anti-quark gives physicists a new window into that relationship. Some theorists believe this connection is meaningful, that the top quark's extreme mass and extreme Higgs coupling are not accidents, that there is something special about the top quark that points toward physics the Standard Model was never designed to describe. The textbooks will be rewritten. That part is already settled. What those revised textbooks will say about the deeper significance of toponium depends on what comes next, and what comes next is a completely different kind of mystery, one that has been building for years inside 650 billion separate collisions. You already know that atoms are small. An atom of hydrogen is about 1/10 billionth of a meter across. That is invisible to any microscope that uses light. Electrons orbiting that atom are smaller still. The proton at the center is roughly 100,000 times smaller than the atom itself. And then there is toponium. The estimated size of a quasi-bound top quark system is about 60 times smaller than a proton. To put that in units you can feel, if a proton were the size of a marble, toponium would be smaller than a grain of pollen. If you scaled a proton up to the size of a football field, toponium would be smaller than a textbook sitting on the 50-yard line. This is the smallest composite object ever directly observed in any physics experiment in history. And it lives for 230 yoctoseconds. A yoctosecond is 1/septillionth of a second. There is no human experience that gets anywhere near that timescale. The fastest camera ever built captures images at roughly 1 attosecond per frame, and 1 attosecond is still about 1 million times longer than a yoctosecond. Billions of toponium systems blink in and out of existence every second inside the Large Hadron Collider. Every single one of them forms and disintegrates before any measuring device could possibly react. The only way physicists detected it at all was by analyzing the statistical shape of the collision data. Across hundreds of millions of events, the presence of the quasi-bound state shifts the distribution of measured energies by a small but consistent amount. They were not seeing individual toponiums. They were seeing the shadow that many invisible events cast across a mountain of numbers. This is what modern particle physics actually looks like. You cannot photograph a subatomic particle. You cannot stop one and examine it. You infer its existence from the patterns it leaves behind in data the size of entire libraries. The fact that physicists managed to detect a particle this small, this short-lived, through statistical analysis of this kind of data, is itself a remarkable achievement. It required detectors precise enough to track thousands of particles per collision, computing systems fast enough to filter billions of events per second, and analysis techniques refined over decades of work. Toponium is confirmed, the smallest, the most massive composite particle ever found, and it existed for the briefest moment physics has ever captured. What the Large Hadron Collider found next was something completely different, a crack in the data, a signal in a decay so rare it happens only once in a million tries, a pattern that 650 billion collisions could not erase. Particle physics has a strategy for hunting things it cannot see directly. If a particle is too heavy to create in a collision, you wait for it to show up as a ghost. Every heavy particle, even one too massive for any collider to produce, can briefly flicker into existence inside a quantum calculation. It appears as what physicists call a virtual particle. It exists for a moment so short it violates the rules of energy conservation, which quantum mechanics allows on those timescales. And while it exists, it nudges the outcome of the calculation. Those nudges are detectable. They show up as tiny shifts in how often certain decays happen, and in the angles of the particles flying out. If the numbers come out different than the Standard Model predicts, a virtual particle from beyond the theory is leaving its fingerprint. The trap physicists built to catch these fingerprints is called the B meson. A B meson is a composite particle containing a bottom quark, paired with a lighter antiquark. They are produced in enormous quantities at the Large Hadron Collider. Most of the time, B mesons decay in predictable ways that match the Standard Model perfectly, but occasionally They decay through a rare pathway that is extraordinarily sensitive to any virtual heavy particles hiding in the background. The specific pathway physicists care about involves a B-meson transforming into a kaon, a pion, and two muons. This process is called an electroweak penguin decay, a name that comes from the bizarre shape of the diagram physicists use to draw the quantum calculation. The actual physics involves a bottom quark changing its identity through a series of quantum steps that include the brief flickering appearance of virtual particles at the loop level. This decay happens in roughly 1 out of every 1 million B-meson decays. That extreme rarity is exactly the point. The Standard Model's contribution to this process is so small that any new physics hiding at higher energies gets to compete on almost equal footing. The fingerprint of a new particle shows up much more clearly here than in common, everyday decays where the Standard Model dominates the result completely. The LHCb experiment was designed specifically to study processes like this. It sits at one of the 4 collision points along the Large Hadron Collider ring, and its detector is built to track the decays of particles containing bottom quarks with extraordinary precision. Starting in 2011, the team began collecting B-meson decays. Year after year, run after run, billions of collisions translated into a catalogue of rare events. 650 billion B-meson decays, fewer than 1,000 examples of the specific penguin pathway, and inside those 1,000 examples, something did not add up. The numbers were off, consistently, in a direction that pointed towards something the Standard Model had never predicted. The name sounds like a joke, a charming penguin, a electroweak penguin diagram, the kind of phrase that makes you check whether the physicist who said it was being serious. They were completely serious, and the story behind the name is the kind of thing that sticks with you. In the 1970s, a physicist named John Ellis was working through a particularly complicated quantum calculation involving quarks. The diagram he drew to map out the particle interactions had an unusual shape. It had a loop at the top and a long line descending from it. A colleague who saw it said it looked like a penguin. The name was jokingly written into a scientific paper, and it stuck. The name is funny. What the diagram describes is not. A penguin decay is a process where a quark changes its type through a series of quantum steps that involve a loop of virtual particles. That loop is what makes it so sensitive to new physics. Any unknown heavy particle can enter the loop and alter the outcome. The heavier the new particle, the more subtle its effect. But the effect is still there, and in a decay, this rare, subtle effects are detectable. The specific penguin decay the LHCb team was studying involves 5 particles in the final state: 1 kaon, 1 pion, 2 muons, and the angles between those particles, combined with the rate at which the decay happens, carry the fingerprint of whatever quantum processes contributed to it. The Standard Model makes precise predictions for both the rate and the angles. If the numbers match, nothing new is hiding in the loop. If the numbers disagree, something is. By December of 2025, the LHCb team had finished their full analysis of data collected between 2011 and 2018. The rate disagreed with the Standard Model prediction. The angles disagreed. Both discrepancies pointed in the same direction. The statistical significance of the combined disagreement reached 4 sigma, 1 in 16,000 odds that it was a random fluctuation. A separate analysis by the CMS collaboration, using different data and different methods, found compatible results. The 2 independent datasets pointed the same direction. 4 sigma falls just short of the 5 sigma threshold for a formal discovery. But it is far past the level where a physicist can reasonably say the signal is noise. And there was one more piece of the puzzle that made the discrepancy even harder to dismiss. The numbers were pointing towards something specific, a particular type of particle, one that theorists had been quietly discussing as a candidate for years. Before getting to that particle, there is one critical complication. An internal Standard Model process, that some physicists believe could explain the entire anomaly without any new physics at all. And whether that explanation holds up will determine whether the B-meson signal is the biggest discovery of the century or the biggest near miss. To find 1,000 examples of a decay that happens once in a million tries, you need to start with 1 billion B-mesons. The LHCb collaboration did not collect 1 billion. They collected 650 billion. That number requires some context. If you counted 1 B-meson decay per second without stopping, it would take over 20,000 years to reach 650 billion. The LHCb detector processed that many in 7 years. The detector does not see B-mesons directly. It sees the particles those mesons decay into, tracks their paths through layers of sensing material, and reconstructs the original decay from the geometry of what came out. The reconstruction requires matching thousands of particle tracks per collision to determine which ones came from the same parent particle. Every collision at the Large Hadron Collider produces not 1 B-meson, but many. The detector runs while beams cross billions of times per second. Computers filter the data in real time, keeping only the events that look like they contain a bottom quark decay worth studying. The rest is thrown away immediately. Even with aggressive filtering, the remaining data fills enormous storage systems year after year. From 650 billion B-meson decays, fewer than 1,000 passed the cuts for the specific penguin decay channel the team was studying. Those 1,000 events are the entire experimental dataset that produced the 4 sigma anomaly. 1,000 data points, each one representing a B-meson that happened to decay through the rarest pathway in the dataset. Each one reconstructed from a handful of particle tracks, each one carrying a small amount of information about the angles and energies of the final state particles. The team spent months working through systematic uncertainties. Every possible source of error was checked: detector efficiency, simulation accuracy, background contamination from other decay processes that might mimic the signal. Each check came back clean. The discrepancy was not from any known source of measurement error. The result was published in Physical Review Letters in March of 2026. 4 sigma, a disagreement between observation and prediction in the direction predicted by models containing new particles. Since 2018, the LHCb detector has been upgraded. The new version is collecting data at 3 times the rate of the original. By the time the next generation of upgrades is complete in the 2030s, the total dataset will be 15 times larger than the one used for this result. More data means a sharper signal or a fading one. If the anomaly is real, the significance will climb toward 5 sigma and beyond. If it was a fluctuation, it will shrink. But while that data collects, there is one theoretical argument that could make the anomaly disappear without a single new data point. A 4 sigma result sounds enormous, 1 in 16,000 odds of a fluke. That is incredibly unlikely in everyday life. If a weather forecaster told you there was a 1 in 16,000 chance of rain, you would leave the umbrella at home. Particle physics does not work like everyday life. The Large Hadron Collider runs billions of collisions per second. Every one of those collisions produces dozens of measurements. Every analysis searches through thousands of possible signals. When you look at that many numbers in that many ways, a 1 in 16,000 fluke is not surprising. Somewhere in all that data, rare statistical accidents happen regularly. This is called the look elsewhere effect. A single anomaly at 4 sigma, in a targeted search where you predicted exactly where to look and exactly what to expect, is much stronger than a 4 sigma bump found by scanning through thousands of different measurements. The LHCb anomaly lands somewhere between those 2 cases. The channel was specifically targeted based on earlier hints, but the measurement involves multiple observables, which introduces some of the look elsewhere concern. The history of particle physics contains a cautionary example almost everyone in the field knows by heart. In 2015, Both ATLAS and CMS detected an excess in their data involving 2 photons produced at a specific energy. The significance reached 3 to 4 sigma. Around 500 theoretical papers were written within months proposing new particles that could explain it. By the end of 2016, with more data in hand, the excess was completely gone. It was a statistical fluctuation. The B meson anomaly is reinforced by the independent CMS result. 2 separate experiments, 2 separate datasets, pointing in the same direction. That reduces but does not eliminate the possibility of a shared systematic error or a correlated fluctuation. 5 sigma is the gold standard because it corresponds to a 1 in 1.7 million probability. At that level, the look elsewhere effect rarely rescues a disappearing signal. The community requires it for formal discovery precisely because of cases like the 2015 photon bump. The anomaly sits at 4 sigma, strong enough to take seriously, not strong enough to announce a discovery. Every physicist working on it is making the same calculation. Will the next dataset push it higher or lower? There is one other calculation being made quietly in theory offices, a calculation about how large one specific standard model background might actually be. Because if that background is larger than expected, the 4 sigma anomaly evaporates without any new particle required. Every result in particle physics comes with a set of theoretical uncertainties. Numbers that are calculated using the standard model, but cannot be computed exactly, only estimated within a range. Most of the time, those uncertainties are small. They do not threaten the interpretation of the result. The B meson penguin anomaly has one theoretical uncertainty that is large enough to matter. It has a name that sounds like it belongs to a children's book. It is called the charming penguin. The electroweak penguin decay the LHCb team studied involves a virtual loop of particles at its core. The standard model predicts what particles enter that loop. The dominant contribution comes from a top quark in the loop. That contribution is well understood and precisely calculated. But there is a secondary contribution. Charm quarks can also enter the loop. Their contribution is much harder to calculate because charm quarks sit in a mass range where the mathematical tools physicists use for these calculations become less reliable. The calculation requires handling a regime where the strong nuclear force is behaving in a complicated, non-linear way. The result carries a larger uncertainty than most inputs to the final answer. If the charming penguin contribution is larger than current estimates, it would shift the standard model's prediction for the decay angles and rate in exactly the direction that matches what LHCb observed. The anomaly would disappear. No new particle required. Just a standard model process that was harder to calculate than expected. This is the most serious theoretical challenge to the new physics interpretation. Some physicists have argued for years that the charming penguin uncertainty has been underestimated and that once it is properly accounted for, the anomaly shrinks below significance. Recent theoretical work pushed back against this argument. A team working on the formal calculation of charming penguin contributions concluded that even with generous uncertainty estimates, the contribution does not grow large enough to fully account for the observed discrepancy. Their result suggested that the charming penguin, even at its worst-case size, leaves a residual anomaly still pointing away from the standard model. But the calculation is not finished. This is an active area of theory work. Different groups using different methods have reached different conclusions. The uncertainty has not been definitively resolved. So the 4 sigma signal sits inside a field of competing interpretations, real new physics versus a background that was harder than expected. 2 independent experimental datasets pointing in the same direction versus a theoretical uncertainty that cannot yet be fully closed. The 15 times larger dataset coming from the LHCb upgrades in the 2030s will likely settle the experimental side. The theory side may take longer, and while physicists wait for both, a separate experiment confirms something else entirely, a decay so rare it makes the B meson anomaly look almost ordinary by comparison. There is a particle called a kaon It is a composite particle made of one quark and one antiquark, similar to a B meson, but much lighter. Kaons are produced in huge numbers at particle accelerators. They are relatively easy to create and well understood. They have been studied since the 1950s, and inside one particular type of kaon, something happens that physicists had been trying to catch for decades. A positively charged kaon can decay into a positively charged pion and a pair consisting of one neutrino and one antineutrino. The process is allowed by the Standard Model. The math confirms it can happen, but the Standard Model also calculates exactly how often it happens. Fewer than 1 in 10 billion kaons decay this way. To put that in terms that stick, if you converted every person alive on Earth into kaons and watched them decay, you would expect fewer than one of them to decay through this channel. Finding even a handful of these events requires producing kaons at an enormous rate. And running the experiment for years, the Na62 experiment at CERN was built to catch this decay. The team ran for years, producing a continuous stream of kaons and watching what they decayed into. In September of 2024, they published their result. The decay was confirmed at 5 sigma significance, the rarest particle decay ever established at the discovery level in any experiment in history. But the confirmation itself was not what made the physics community take notice. It was the number. The Standard Model predicts a specific rate for this decay. The Na62 team measured a rate about 50% higher than that prediction. 50% is enormous. It is far outside the experimental uncertainty. The gap between the prediction and the measurement is pointing at something the Standard Model did not account for. The Na62 result sits in a unique position. The theoretical prediction for this decay is extraordinarily clean. Unlike the B meson penguin channel, where charming penguin contributions introduced large uncertainties, this kaon decay has very few complicated background processes. The Standard Model's number is precise. When the measured rate comes out 50% too high, there is very little theoretical wiggle room to explain it away. A refined measurement was presented at a physics conference in March of 2026, with significantly reduced uncertainties. The excess held. Additional data from 2026 is still being analyzed. One physicist had been warning for years that exactly these kinds of decays would be where new physics showed up first. He had a name for the 7 most sensitive channels, and his framework for why new physics was hiding in these specific places is unlike anything else in the field. There is a physicist at a university in Munich who has spent decades thinking about where new physics hides. His name is André Buras. His argument is simple and strange. The Large Hadron Collider may be looking in the right place, but at the wrong scale. Buras identified 7 specific particle decays, 7 processes so rare, so theoretically clean, and so sensitive to new physics that he argues they are the primary windows into a layer of reality the Large Hadron Collider cannot reach directly. He calls them the Magnificent 7. The kaon decay that Na62 confirmed is one of them. 2B meson decays involving neutrino pairs are among the others. All 7 share the same properties. The Standard Model predicts their rates with high precision. Any new particle contributes to them through virtual loops, and the theoretical backgrounds are small enough that a deviation from the prediction is hard to explain away. The framework Buras built around these 7 decays connects to something he calls the Zeptuniverse, a regime of physics at distances so small that the Large Hadron Collider cannot probe it directly. The collider reaches down to about 50 zeptometers. 1 zeptometer is 1 sextillionth of a meter. The Zeptown universe Buras describes sits at 1 zeptometer, 50 times smaller. At that scale, new particles and new forces may exist that have never been detected, because creating them directly would require a machine 50 times more powerful than the Large Hadron Collider. Such a machine could not fit on Earth, but those particles would still show up in the Magnificent 7. Virtual effects reach deeper than direct production. A particle that cannot be created in a collision can still flicker into existence inside a quantum loop and shift the rate of an ultra-rare decay. That shift is measurable. That is exactly what Burris predicts these 7 channels can reveal. The kaon decay result from Na62 fits this picture. The B meson anomalies from LHCb fit this picture. Both show deviations in the direction that models with new particles at the Zeptoniverse scale would predict. Burris published his framework before either of these results came in. The fact that the experimental data is now moving in the direction he mapped out does not confirm his theory, but it means his prediction is surviving contact with real data, which in physics is how credibility builds. The Zeptoniverse is a theory, an attractive one, a precise one that ties the anomalies together under a single framework instead of treating each one as an isolated accident. And if that framework is right, then the Large Hadron Collider has been sending signals about a layer of reality it was never powerful enough to see directly. The signals have been arriving for years. The question is whether there is a machine that can go further. One experiment, already approved and under construction, was built to look in a completely different direction entirely. Imagine you are standing in a field, trying to study something buried deep underground. You cannot dig. Your only tools are instruments that measure vibrations through the ground. The deeper the object is buried, the fainter the vibrations. But they are still there, still detectable if your instruments are sensitive enough. That is the situation particle physics is in right now. The Large Hadron Collider smashes particles together at enormous energies. Those energies translate directly into the smallest distances the machine can probe. Higher energy means smaller distances. The collider reaches down to about 50 zeptometers. 1 zeptometer is 1 sextillionth of a meter. A proton is about 800 zeptometers across, so the collider is probing distances far smaller than a proton, which is already an astonishing achievement. But Burris argues the interesting new physics lies at 1 zeptometer, 50 times deeper, 50 times smaller than anything the Large Hadron Collider can directly reach. To probe 1 zeptometer directly, you would need a particle accelerator roughly 50 times more powerful than the current one. To fit a machine that powerful into a circle, using the best magnet technology available, the tunnel would need to be thousands of miles around. That machine cannot be built on Earth. So the Zeptone universe sits just beyond the reach of any machine humanity could realistically construct in the foreseeable future. And yet the signals from it are showing up anyway. Virtual particles do not obey the same energy limits as real ones. In quantum mechanics, a particle can briefly borrow energy from the universe, flicker into existence at a mass far above what a collider can produce, affect the quantum calculation it appears in, and vanish before the debt comes due. This is not a loophole. It is a fundamental feature of quantum field theory. It is how the charming penguin contributes to B meson decays. It is how any undiscovered heavy particle leaves its mark in the Magnificent Seven. Particles living at the Zeptown universe scale would do the same thing. They would appear in loops, shift the rates of ultra-rare decays by measurable amounts, and leave fingerprints in precisely the channels that Burris identified. The kaon decay measured 50% above the standard model prediction. The B meson penguin anomaly at 4 sigma, both pointing in the direction Zep2 nervous models would predict. Neither result is confirmed beyond the 5 sigma threshold. Both remain in the space between strong evidence and settled fact. But both fit the same framework. 2 independent experiments, 2 independent particle species, 2 independent decay channels, all showing the same direction of deviation. If the Zeptoniverse framework is right, humanity has been receiving signals from a layer of reality it cannot visit, faint echoes from physics 50 times deeper than the deepest probe ever built. Whether those echoes represent new particles, new forces, or something with no name yet in any theory is a question that will not be answered quickly. But one experiment was designed with a completely different approach to finding the answer. For 30 years, one particle promised to solve 3 of the biggest problems in physics simultaneously. It would explain why neutrinos have mass. It would provide a candidate for dark matter, and it might explain why matter beat antimatter after the Big Bang. Physicists called it the sterile neutrino. To understand what makes it sterile, start with the three neutrinos the Standard Model already describes. These are real, confirmed particles. They interact with matter through the weak nuclear force, which is why they are so hard to detect. A neutrino produced in the Sun travels straight through the entire Earth, with only a tiny chance of interacting with a single atom. They are ghostly, but they do interact, just very rarely. A sterile neutrino would be different. It would have mass, which the Standard Model's ordinary neutrinos also have, but it would feel none of the known forces except gravity. No weak force interaction at all. A sterile neutrino could pass through a lead wall a light year thick without touching a single atom. The appeal of this particle was enormous. Adding one sterile neutrino to the theory, with the right properties, could fix the neutrino mass problem through a mechanism called the seesaw, where the mass of known neutrinos is linked to the mass of the sterile partner in a way that naturally produces very small values. It could also provide a dark matter candidate, since a particle that interacts only through gravity and mass effects would clump around galaxies without emitting any light. Multiple experiments had detected hints supporting the sterile neutrino's existence. The LSND experiment in New Mexico found an anomaly in 1995 that seemed consistent with neutrino oscillations involving a fourth neutrino type. The Mini-Buoy experiment confirmed a similar anomaly years later. The pattern of evidence was not conclusive, but it was persistent enough to keep the sterile neutrino hypothesis alive through decades of discussion. Then came micro-Buoy. The micro-Buoy detector at Fermilab in Illinois was filled with 170 tons of liquid argon, cooled to -303 degrees Fahrenheit. When a neutrino passes through liquid argon and interacts, it leaves an ionization trail, a track of electrons knocked loose from argon atoms. The detector reads those tracks with enough precision to reconstruct the neutrino's path and energy. The team ran 2 separate neutrino beams through the detector, 2 independent datasets, 2 separate chances to see the sterile neutrino signature. The result, published in Nature in December of 2025, was definitive. The data ruled out the simplest sterile neutrino model with 95% certainty. One door closed. Firmly, after 30 years. Closing a door in science sounds like failure. It rarely is. Micro-Buoy did not prove that sterile neutrinos do not exist. It proved that the simplest possible version of the theory, one sterile neutrino with specific properties that would have explained the LSND and Mini-Buoy anomalies, does not match the data. That distinction matters enormously. The LSND and Mini-Buoy anomalies are still real. They have not been explained. Those experiments saw something in their neutrino data that does not fit the 3 neutrino Standard Model picture. Micro-Buoy's result eliminates the single sterile neutrino as the explanation, but the anomaly itself remains. Something caused those earlier signals. The single sterile neutrino was the simplest candidate. Its elimination means the explanation, if one exists, is more complex. 2 sterile neutrinos, 3 sterile neutrinos, a sterile neutrino with different mass or mixing parameters than the simple model assumed. All of these remain open. The micro-Buoy result explicitly states that more complex sterile neutrino scenarios are consistent with its data. The next generation of experiments will probe those scenarios directly. The deeper problem, neutrino mass itself, remains completely unsolved. Neutrinos have mass. The Standard Model says they should not. Some mechanism gives them that mass, and that mechanism is currently unknown. The sterile neutrino was one attractive solution. Its simplest form is now ruled out. The mechanism is still missing. There is a further question beneath that one. Ordinary matter particles come in 2 distinct forms, particle and antiparticle. An electron and a positron are distinct, but there is a theoretical possibility that a neutrino might be its own antiparticle. If a neutrino and an antineutrino are the same object, neutrinos are called Majorana particles. If they are distinct, they are called Dirac particles. This question is completely open. No experiment has answered it. The answer would directly reveal the mechanism behind neutrino mass and might expose the source of the matter-antimatter imbalance that allowed the universe to exist. Ruling out the simple sterile neutrino model cleared the field. The harder problems now stand more exposed, without an easy answer in front of them. And while neutrino physicists process that result, a completely different team at CERN is preparing an experiment that takes a totally different approach to the same set of mysteries. Everything you can see, touch, or stand on is made of protons, neutrons, and electrons. Protons and neutrons are built from quarks. The standard model predicted from the start that neutrinos should have zero mass. That prediction was built into the mathematical structure of the theory from the ground up. Then experiments watched neutrinos change type as they traveled. An electron neutrino created in the Sun arrived at Earth partly transformed into muon neutrinos and tau neutrinos. This behavior, called oscillation, is only possible if different neutrino types have different masses. Zero-mass neutrinos cannot oscillate. The data was unambiguous. Neutrinos have mass. The standard model was wrong about something fundamental. This matters beyond fixing one equation. The mechanism that gives neutrinos their mass is likely connected to a larger structure of physics the standard model never describes. The leading candidates for that mechanism involve either a Majorana mass term, requiring neutrinos to be their own antiparticles, or a seesaw mechanism requiring partner particles at very high energies. Both possibilities point toward physics at a scale the Large Hadron Collider may never directly reach. The connection to human existence runs deeper still. The matter-antimatter asymmetry that allowed the universe to be made of matter rather than pure radiation may have originated in the neutrino sector. A process called leptogenesis proposes that in the early universe, heavy partner particles of the neutrino decayed in a way that slightly favored matter over antimatter. That tiny imbalance then cascaded into the matter-dominated universe we live in today. If leptogenesis is correct, the reason you exist is written in the mass and mixing properties of the neutrino. The mechanism that gives them mass is the same mechanism that made the universe survivable for atoms, stars, planets, and people. No experiment has confirmed leptogenesis. The required partner particles have never been detected. The connection is a theory, an attractive and well-developed one, but a theory. What makes it testable is a new experiment designed to find the lightest versions of those partner particles directly, an experiment that does not use high-energy collisions at all. The Large Hadron Collider operates on one core idea: go to higher energies, smash particles together harder. If a new particle has a mass within the machine's reach, the collision will create it. This strategy worked. It found the Higgs boson. It produced toponium. It created more B mesons than any experiment in history. But it has also spent 15 years failing to find supersymmetric particles, extra dimensions, or any direct sign of the new physics the standard model's failures demand. Every search for heavy new particles has come back empty. Some physicists started asking a different question. What if the missing particles are not heavy? What if they are light but almost invisible? What if they interact so weakly with ordinary matter that even billions of collisions per second at the highest energies ever achieved cannot produce enough of them to see? This is the intensity frontier, the search for particles that are light and feebly coupled. Hard to create, harder to detect, almost impossible to find with a machine designed to hunt heavy things. The SHIP experiment, which stands for Search for Hidden Particles, was formally approved by CERN in March of 2024. It brings together 54 research institutes from 18 countries. It will be built in an existing experimental hall in CERN's North area and will use a proton beam from the superproton synchrotron, a smaller accelerator that predates the Large Hadron Collider by decades. The setup is different from anything at CERN's main ring. Protons slam into a dense fixed target, not into each other. The collision produces a spray of particles, most of them familiar standard model products. Heavy shielding blocks everything known. Hundreds of feet of material stop every particle the standard model predicts. Whatever makes it through is something the shielding was not designed to stop, and anything the shielding was not designed to stop is, by definition, unknown. The detector waits on the other side of the shielding in a region designed to have essentially zero background from known particles. If anything registers in the detector, it came from somewhere the standard model does not account for. Construction begins in 2027. Data collection starts around 2030 to 2031. The particles SHIP is hunting are unlike anything the Large Hadron Collider was built to find. And if even one of them shows up, it solves multiple mysteries at once. The engineering challenge behind SHIP is enormous. The goal is to create a region of space inside a detector where every particle the standard model predicts has been completely eliminated, zero background. Any signal that appears must come from something new. The first layer of filtering is the target itself. Protons hit a dense block of material chosen to maximize the production of heavy flavor particles like charmed mesons and beauty mesons, the same parent particles that decay into feebly interacting species. The target also stops the proton beam completely, so none of it reaches the detector. The second layer is a muon shield. Muons are heavy versions of electrons, and they punch through material more easily than almost any other particle. A standard shielding wall would stop electrons, pions, and kaons, but let millions of muons through. SHIP uses a specially designed magnetic shield that bends muon paths away from the detector volume, sweeping them out of the way rather than trying to absorb them. The third layer is the decay volume. This is a large evacuated region, roughly the length of 2.5 football fields, where the feebly interacting particles produced in the target would travel before decaying. Known particles either decay too quickly to reach this region or are already blocked. The hidden particles the experiment is hunting would survive the journey and decay visibly inside the volume. The fourth layer is the detector itself. Surrounding the decay volume are sensors that reconstruct the tracks of any particles produced by a decay inside the volume. The geometry of the decay products tells physicists the mass and identity of the parent particle. The entire system is designed around one requirement: the expected number of known standard model events passing all cuts and reaching the detector is essentially zero. The team calculated that over the planned run, fewer than one background event should contaminate the data. In particle physics, zero background means any detection is a discovery. You do not need a 5 sigma threshold when the noise floor is zero. One clean event inside the decay volume, reconstructed as a particle with a mass the standard model does not predict, is a confirmed new particle. SHIP does not need to collect hundreds of trillions of events to find what it is looking for. It needs one. What it is specifically designed to find are particles that appear in several theoretical frameworks as the answer to problems the Large Hadron Collider has been unable to crack. SHIP has a target list. Specific particles predicted by specific theories, each one a candidate answer to a question the standard model cannot touch. The first is the dark photon. In the standard model, the photon is the particle that carries the electromagnetic force. Ordinary photons interact with any particle that carries electric charge. A dark photon would be similar but connected to a hidden sector of particles rather than to ordinary charged matter. It would interact extremely weakly with standard model particles, which is why no experiment has detected it. The interaction is not zero, just tiny. Dark photons produced at CERN would travel long distances before decaying into pairs of electrons or muons. SHIP's decay volume and detector are sized precisely to catch those decays. The second target is the heavy neutral lepton. This is the particle that connects most directly to the neutrino mass problem. A heavy neutral lepton would be a massive partner to the known neutrinos. It would interact through the weak force but with much smaller strength than ordinary neutrinos. The seesaw mechanism that could explain the small masses of known neutrinos requires partners at high mass. If those partners exist in the mass range ship can reach, between a fraction of a proton mass and a few proton masses, the experiment will find them. Heavy neutral leptons are also the particles needed for leptogenesis, the process that may explain why matter won over antimatter. The third category is dark scalars. These are particles similar to the Higgs boson, but connected to dark matter rather than to ordinary mass generation. All three of these particle types share a critical property. They are theoretically predicted to appear in frameworks that simultaneously solve dark matter, neutrino mass, and the matter-antimatter asymmetry. A single confirmed detection in any of these categories would not be an isolated discovery. It would be a key that unlocks three locked rooms at once. The mass and coupling ranges ship can probe have never been fully explored by any previous experiment. The intensity frontier is genuinely new territory. Something else entirely may already be leaving its fingerprint in existing Large Hadron Collider data. A particle that would not just explain the B-meson anomaly, but shatter the boundary between two families of matter that physicists have treated as completely separate for 60 years. The Standard Model divides all matter particles into two distinct families, quarks and leptons. Quarks are the building blocks of protons and neutrons. They feel the strong nuclear force. They come in 6 types and always appear in groups inside composite particles. Leptons are a separate family. They include the electron and its heavier cousins, plus the 3 types of neutrinos. Leptons do not feel the strong force. These two families have been treated as completely separate since the Standard Model was assembled in the 1960s. There is no Standard Model particle that belongs to both groups simultaneously. No particle that can transform a quark directly into a lepton. The separation is built into the mathematical structure of the theory. A leptoquark would break that separation. A leptoquark carries both quark and lepton quantum numbers at the same time. It can turn a bottom quark into a muon, or a top quark into a tau lepton. Depending on its properties, it can interact with specific combinations of quarks and leptons and ignore others. The idea is not new. Leptoquarks appear naturally in certain grand unified theories, frameworks that attempt to merge the strong nuclear force with the electro-weak force into a single mathematical structure at very high energies. In those theories, quarks and leptons are related at some deep level, and the leptoquark is the particle that carries that relationship. The reason leptoquarks became a topic of intense discussion recently is the B-meson anomaly. The specific decay channel showing the 4 sigma discrepancy involves a bottom quark transforming into particles, including muons. A leptoquark coupling to that combination of particles would alter that decay rate in exactly the observed direction. Multiple theoretical analyses identified a specific type of leptoquark, one with particular quantum numbers called a vector leptoquark, that could simultaneously explain the B-meson anomaly, the matter-antimatter measurements, and other subtle hints from lepton physics, all with a single new particle of the right mass. The mass that fits these models is estimated to sit several times higher than the proton mass in energy units, placing it at or beyond the edge of what the Large Hadron Collider can directly create. Direct searches for leptoquarks have set limits, between roughly 1 times proton mass and 1 3/4 times proton mass. Depending on the coupling strength and quantum numbers, leptoquarks with those properties have been excluded at high confidence. Above that range, the search is ongoing. But while the direct searches continue, something else happened in early 2026 that electrified the field. The reason leptoquarks show up in the B-meson analysis is the same reason any undetected heavy particle can leave a fingerprint in rare decays. They appear in loops. Quantum field theory allows particles that are too heavy to be created directly in a collision to briefly appear inside quantum calculations. They exist as virtual particles for a moment too short for energy conservation to apply, affects the calculation they enter and vanish. The heavier the particle, the more briefly it appears, and the smaller its effect on the final result. For ordinary decays that happen frequently, this effect is swamped by the dominant Standard Model processes. The Standard Model contribution is huge. A small virtual correction from a new heavy particle is invisible by comparison. The electroweak penguin decay that LHCb studied is different. The Standard Model's contribution to this channel is tiny. The decay happens once in a million B mesons. At that level of rarity, a virtual leptoquark with the right quantum numbers contributes at a rate comparable to the Standard Model itself. The two effects compete, and that competition shifts the measured rate and angles away from the Standard Model prediction. This is exactly what was observed. The angular distribution and rate both shifted. The shift pointed in the direction predicted by vector leptoquark models. 4 sigma separated the observation from the Standard Model prediction. The analysis requires a leptoquark with very specific quantum numbers. It must couple to the bottom quark and to muons with a particular combination of properties. Different leptoquark types with different quantum numbers would shift the B meson observables in different directions. The fact that the observed shift matches predictions for a specific class of models is not proof, but it narrows the field of candidate explanations considerably. If the leptoquark interpretation is correct, the signal should strengthen with more data. It should also appear in related decay channels with specific predicted magnitudes. The LHCb team is already searching those channels. Consistency across multiple channels would be much harder to explain as a statistical accident or a theoretical misestimate. The leptoquark also predicts effects in other experiments. Searches for the particle's direct production continue at higher energies. Precision measurements of muon behavior provide another indirect test. All of these searches are running simultaneously, and then in early 2026, a report appeared claiming the search was over. In March of 2026, a report appeared online claiming that the LHCb collaboration had confirmed a leptoquark signal in run-3 data at 5 sigma, the gold standard, the threshold that separates evidence from discovery. If true, it would be among the most significant results in the history of particle physics, a particle that breaks the boundary between quarks and leptons. A direct confirmation that the Standard Model's family separation is wrong. The physics community did not celebrate. Official CERN press releases listed no such announcement. Physical Review Letters, the journal where major particle physics discoveries are formally published, carried no corresponding paper. The major physics news outlets that cover Large Hadron Collider results reported nothing confirming the claim. The Particle Data Group, which maintains the official registry of confirmed particles, made no update. The report originated from a single source and had not been independently verified through the peer review process that particle physics requires before any result is treated as established. This is not how discoveries work in particle physics. A 5 sigma result at the Large Hadron Collider goes through internal review by the collaboration, which for LHCb involves hundreds of physicists. It is then submitted to a peer-reviewed journal. It is publicized through official CERN channels. The process takes months and is visible. A genuine discovery at 5 sigma does not appear first in a single online report without any accompanying official announcement. This is a confirmed unknown. The claim exists. Its origin is real. Whether the physics behind it is real has not been established as of May 2026. Treating it as confirmed would be wrong. Ignoring it entirely would also be wrong. It sits in the space that particle physics knows well, compelling, unverified, waiting for the process to catch up. The matter-antimatter question does not wait for any single result. It is the oldest open problem in the field, and the evidence on that front has been building from a completely different direction. After the Big Bang, the universe should have created matter and antimatter in perfectly equal amounts. equal quantities, equal energies, occupying the same space. Within a fraction of a second, every particle should have found its antiparticle partner, and the two should have collided and annihilated into pure light. The universe should be empty, a vast field of radiation with no atoms, no stars, no planets, nothing. You are here. Which means the equal balance was broken. Physicists call this broken balance CP violation. The letters stand for charge conjugation and parity, two symmetry operations in physics. When combined, they predict that a particle and its antiparticle should behave identically under a mirror transformation. CP violation is when that symmetry breaks, when matter and antimatter behave slightly differently. It was first detected in the 1960s inside neutral kaon decays, a tiny asymmetry, a fraction of a % difference between the behavior of certain kaon states and their antimatter equivalents. The discovery earned a Nobel Prize and opened a new field of physics. Since then, CP violation has been confirmed in several other systems. B mesons showed CP violation, confirmed at the Stanford Linear Accelerator Center in 2001 and at the KKK Accelerator in Japan around the same time. The LHCb collaboration later observed CP violation in D mesons, composite particles built around charm quarks. Every confirmed instance of CP violation adds to the catalogue, and every instance also adds to the problem. The total amount of CP violation contained in every confirmed measurement, added together across all systems, is many orders of magnitude too small to explain why matter dominates the observable universe. Orders of magnitude means factors of 10 multiplied repeatedly. The gap is enormous. The known sources of asymmetry account for a tiny fraction of what must have existed in the early universe to produce the matter-dominated cosmos we inhabit. This means one thing: unknown sources of CP violation must exist in nature. Somewhere in the physics the standard model cannot describe, there are processes that created the asymmetry large enough to produce everything that exists. Finding those processes is one of the primary reasons CERN was built. In July of 2025, the LCCB collaboration published a result in Nature that extended CP violation into a new domain. For the first time, matter-antimatter asymmetry was confirmed inside a baryon decay. Baryons are the family of composite particles that includes protons and neutrons. Every atomic nucleus is built entirely from baryons. Every proton in every atom in your body is a baryon. They are the building blocks of all visible matter in the universe. CP violation had been observed in mesons, composite particles made of one quark and one antiquark. Mesons are abundant, and their decays are easy to study at the Large Hadron Collider. But mesons are not what visible matter is made of. Baryons are. The LHCb result showed a small but statistically significant difference between the decay of a specific baryon and the decay of its antimatter partner, the corresponding antibaryon. The rates were different. The angular distributions of the decay products were different. The difference was real. This is historically significant. Baryons are the particles that won the matter-antimatter war, proving that they carry CP violation, that their behavior differs from their antiparticle partners, even in small ways, directly connects the matter-antimatter mystery to the particles that actually make up ordinary matter. The question is whether the measured asymmetry is large enough. It is not. The standard model predicts a small amount of CP violation in baryon decays, and that is what was found. Matching the prediction, confirming the effect exists, is an important experimental milestone, but the confirmed asymmetry is still many orders of magnitude below what the early universe required. The same problem repeats itself across every measurement. Real asymmetry, confirmed asymmetry. Nowhere near enough asymmetry. The missing CP violation is not a rounding error. It is a vast gap pointing toward physics that has never been detected. The standard model accounts for a small fraction of the required asymmetry and has no mechanism for the rest. Every experiment that confirms CP violation within standard model predictions simultaneously sharpens the edge of that gap, and the gap is telling the same story as the B-meson anomaly, the kaon decay excess, and the Zeptuniverse framework. Something that has not yet produced a clean 5 sigma signal in any direct search. The hunt for that unknown may require going further than any accelerator in history has ever reached. Stand in front of a puzzle. You have assembled the edge pieces. You have filled in most of the middle. And then you realize that the remaining pieces left in the box account for maybe 1% of the total area of the image. The rest of the picture, 99% of it, is missing. Not just unfinished, missing from the box entirely. That is the situation with CP violation in the standard model. All known sources of CP violation, every measurement ever confirmed in every experiment ever run, add up to a number that falls enormously short of what the early universe required. The leading theoretical estimates suggest the known CP violation is off by many orders of magnitude. The gap is so large that it cannot be blamed on measurement uncertainty or theoretical imprecision. The known physics simply does not add up to a universe full of matter. Physicists have known this for decades. The gap is not new. What is new is that the experiments probing the edges of that gap are now finding deviations, small signals that consistently point away from the standard model. The B-meson anomaly, the kaon decay rate 50% above prediction, the baryon CP violation confirming the standard model exactly, while simultaneously proving the known amount is insufficient. Each result is a data point on a map. None of them alone identifies the destination. Together, they trace the outline of something that has no name yet in any confirmed theory. Grand unified theories predict new sources of CP violation at very high energies. Leptogenesis requires heavy partner particles that carry enormous CP violating phases. Leptoquarks introduce new couplings between quarks and leptons that bring their own CP violation. Any of these could be the missing source. All of them require physics beyond the standard model. The missing CP violation is the deepest version of the question the Large Hadron Collider was built to answer. Why does the universe exist rather than an empty field of radiation? No confirmed discovery has answered it yet, but the tools to answer it are either already running or already approved and under construction. And one proposal in particular would give physicists access to energies no human-built machine has ever reached. The Large Hadron Collider sits in a tunnel 53 miles in circumference, buried under the border of France and Switzerland. It accelerates protons to energies of 13 to 14 trillion electron volts and smashes them together. It is the most powerful particle accelerator ever built. CERN wants to build something 3 times larger. The Future Circular Collider is a proposed accelerator with a tunnel roughly 56 miles in diameter, or about 90 miles around. Its first phase would collide electrons with positrons at energies tuned precisely to study the Higgs boson and other particles in detail, far beyond what the Large Hadron Collider can achieve. This phase would act as a precision factory, producing millions of Higgs bosons per year and measuring their properties to levels of accuracy that might reveal indirect signs of new physics hiding in the Higgs sector. The feasibility study for this machine was published in March of 2025. CERN's governing council reviewed it in November of 2025 and confirmed no fundamental technical barriers to construction. The second phase would insert proton beams into the same tunnel and collide them at 100 trillion electron volts, 7 times higher than the Large Hadron Collider's current energy. At that energy, particles produced in the collision would carry enough mass to probe distances deep into the Zeptoniverse, the regime Buras identified as where new physics is hiding. Particles that the Large Hadron Collider cannot create would be produced directly. Leptoquarks in the multi-TeV range, new sources of CP violation, possibly the heavy partner particles needed for leptogenesis. The electron-positron phase is targeted for completion around 2045, a assuming construction approval comes in the early 2030s. The proton-proton phase would not begin high-energy physics until around 2070. 2070 is not a typo. The physics the second phase is designed to reach requires a machine that will not be ready for nearly half a century. The questions being chased are that hard, the answers are that far, and the timeline between now and then is filled with experiments that could change everything before the big machine turns on. Some questions in physics have answers coming within years, others will take generations. The nearest deadline is 2030 to 2031. That is when SHIP begins collecting data. If hidden particles in the mass range between a fraction of a proton mass and a few proton masses exist and interact at the coupling strengths theoretical models predict, SHIP will find them. The experiment does not require years of accumulated data to reach significance. Its near-zero background design means any clean signal in the detector is immediately meaningful. The question of whether light feebly interacting particles exist could be resolved within the first years of SHIP's operation. The next major dataset comes from LHCb. The upgraded detector has been collecting data at 3 times the rate of its predecessor since 2018. By the 2030s, a second upgrade will push that to 15 times the original rate. The B meson penguin anomaly currently sits at 4 sigma. More data either pushes it to 5 sigma or reveals it as a fluctuation. The answer may arrive before 2035. The Na62 kaon decay measurement will accumulate additional data through the mid-2020s. The excess above the standard model prediction, currently 50% with significant uncertainty, will either sharpen into a clear deviation or dissolve into consistency. That result could land within a few years. By around 2045, if the Future Circular Collider's first phase is approved and built on schedule, physicists will have a precision Higgs factory, measurements of the Higgs boson's properties at levels 20 times more accurate than anything the Large Hadron Collider can achieve. If new physics couples to the Higgs with any detectable strength, this phase will find the fingerprints. The deepest questions, direct confirmation of the zepto-nuverse, the mechanism behind leptogenesis, the identity of the particle responsible for dark matter at high mass, those may require the proton-proton phase that begins around 2070. Half a century of experiments, each generation of physicists handing the puzzle to the next, each step bringing the answer closer without any guarantee of what the answer will be. Every chapter in this video has circled the same moment, a moment that has not happened yet. The moment when one of these signals crosses the 5 sigma threshold and stays there, when 2 independent experiments confirm the same new particle in the same dataset with no theoretical escape route left. What happens then? In the short term, the confirmation triggers a cascade of questions rather than answers. Every new particle comes with properties: mass, charge, spin, how it interacts with each force. Each property carries information about the theory it belongs to. A confirmed leptoquark would immediately demand an explanation for why it couples to the specific quarks and leptons it does. A confirmed heavy neutral lepton would demand a measurement of its mass and mixing angles. A confirmed dark photon would demand a search for the hidden sector it connects to. The standard model would not simply be replaced, it would be extended. The new particle would fit into a larger framework, one that contains the standard model as a special case and adds new structure around it. Theorists would spend years working out the implications. Which model does the data favor? What other particles does that model predict? Where should the next search look? But the deeper consequence runs further. Every question the standard model cannot answer right now, dark matter, neutrino mass, the matter-antimatter gap, all of them are connected. They do not appear to be separate problems with separate solutions. The same candidate particles keep appearing across all 3. A heavy neutral lepton that solves neutrino mass also enables leptogenesis. A leptoquark that explains the B meson anomaly also introduces new CP violation. A dark photon that mediates dark sector interactions also couples to a broader hidden symmetry. If any one of these particles is confirmed, it most likely belongs to a framework that connects to all the others. Finding one is finding the door. Behind it are the rest. The universe exists because something tipped the balance between matter and antimatter by an amount too small for any current theory to explain. The mechanism behind that tip is unknown. The particle that carried it has never been detected. Every experiment in this video is a different approach to the same locked room. The door is close. The signals are converging. The next few years may be the most important in particle physics since the Higgs boson was found in 2012. Or the signals may fade, and the search continues. Either way, the machine under the mountains keeps running.